Welcome back. In this lecture, we will describe breadth-first search. Now, breadth-first search treats the frontier nodes as a queue. So it's always going to select the earliest element that was added to the frontier. It's not going to dive down deep into the search space like depth first, but it's going to be checking out all of the neighbors of a given node. And so let's give an example again. So we start out with node 1. And then we're going to expand out the neighbors of node 1. So we expand out node 2 and node 3. Neither of them are goals. So we are going to, and we've expanded out everything that's a neighbor of node 1. So we don't need to revisit it. So then what we're going to do is let's go and look at the first node that was added to the frontier, and that is this guy here, node 2. So node 2 expands out to 4 and 5. Again, no goals. So then we're going to look at now the oldest node in the frontier. 4 and 5 are just expanded, and 2 is totally expanded, so we're going to check out 3. So expanding 3, we get 6 and 7. Still nothing. Now note here as I go along, I'm not throwing anything out. I got to retain all these nodes. And not only do I need to keep the nodes that I expanded that are in the frontier, 4, 5, 6, and 7, I need to keep nodes 1, 2, and 3, even though I'm not expanding them anymore. Reason being is that 1, 2, and 3, any one of those, or a couple of them, could be in the solution, and I don't know which ones. So I don't know if the solution, for example, between 2 and 3, I have no idea if the solution is going to be, down below 2 somewhere or down below 3 somewhere. So anyway, back to the frontier set. The oldest thing I had was 4, so I'm going to do 8 and 9. They're not goals. So then I'm going to expand out the neighbors of 5, which is 10 and 11, and I do the same for the other elements of the frontier. So now I have on the frontier nodes 8, 9, 10, 11, 12, 13, and 14. So I'm going to go and look at the oldest one, which is 8. And I get 15 and 16. Neither of them are goals. So now I'm going to look at node 10. And I expanded out, and congratulations, we got this orange node, so we have now arrived at a goal node. Now, when you look at this and you think about depth-first search, if we're talking about optimality in terms of number of hops in the graph, we actually have a provably optimal solution. But we've gotten there with not only exponential runtime, but an exponential space requirement. Because, like I said, we had to maintain all of the nodes because we didn't know if it was going to be node 2 or 3. And we didn't know if it was going to be node 4, 5, 6, or 7, and so on. The other thing looking at this is notice how the number of nodes in the frontier is increasing as I go through the nodes that were previously in the frontier. It's constantly expanding, and that's because that's why you have the name breadth-first search. The tree is getting wider. So a quick exercise. So which of the shaded gold nodes would it reach first? So again, depending on if you're going left to right or right to left, you're going to reach either C or A. So notice you get these a lot faster, or you get these a lot shallower depth as opposed to depth-first search, which would end up giving you, something like node D down there. But you don't know how soon you're going to reach that, and and again, the cost of maintaining all those old nodes increases the more you peruse that search space. And so does it guarantee to find a path with the fewest arcs? Absolutely. But what happens with infinite graphs or graphs with cycles if there is a solution? Well, here, it does have the potential to not terminate. But, you don't have the same type of risks in, going in kind of this attractor that depth first search has. And so time complexity and space complexity, they will both be exponential. And how does the goal affect the search? Well, again, if the goal isn't as deep and you don't have to expand too much to get there, you're going to find it right away. But the deeper the goal, that expense mounts and mounts because it'll be exponential. So lowest cost first search is a generalization of breadth first search, where now we have a cost value associated with each arc, as opposed to treating each arc as the same cost. So an optimal solution is just one with where this number is the lowest. And so with lowest cost first search, at each stage, select the path on the frontier that has the lowest overall cost. And the frontier, again, is a priority queue, but now it's ordered by cost instead of what was most recently added. And so the first path to the goal node is the one with the least cost. And when arcs are equal, then this reduces to breadth first search. And so, here's kind of a summary of the uninformed search strategies that we've looked at in this course. With regard to completeness, meaning that it can find a goal, breadth first search and lowest cost first search are guaranteed to find a solution. Depth first search not. However, they all could potentially have trouble halting, and they all have exponential runtime. Depth first search is better on the space requirement because it's only linear space. So in future lectures, we're going to look at how to address these problems by leveraging additional information about the problem. Thank you again.